much. Thank you very much, Manuel, for this very kind introduction. Thank you very much for the invitation. Indeed, when I listen to that, I hear that I'm already a while in the business, and when I thought about what would be a good thing to tell you in this keynote, I decided not to talk too much about concrete and practical projects and things like that, but more on the challenges and the findings that we could generalize out of that. And the challenge is indeed what needs to be done in the systems engineering domain and in the connected software and systems engineering domain in the future much more. And you know, probably, and a lot of us are in this area more or less active in the Internet of Things, cyber physical systems domain, where software is not isolated on the computer in itself, but the whole thing has to be thought about holistically. And one important organization that we deal with is Interdisciplinary. They have a nice definition of what systems engineering actually is. And if you look at this, you don't have to read everything here, but the important things are that the whole thing is that we look at it holistically. We have to understand the stakeholder needs. If we look at all these things, we have to explore possibilities, opportunities and things like that. We have to document, we have to map that down to a design, synthesize, finally, not only the code, but also the physical gadget and the whole thing together. We have to verify and validate that the whole thing works, and we have to evolve it over time, because in particular, for example, if you look at the car manufacturers, they know already today in how many years they will make the next update. So evolution is for them an important thing, which also brought us to a lot of development processes. The V model is particularly well known in Germany, although it came from the US, and you see different variants of the V model here from Interdisciplinary or for the US Department of Transportation, but also rational unified process. And the middle picture shows a little bit how our more mechanical oriented colleagues try to bring agility into it, where they first think about the system in a very virtual way. So a lot of software is involved on both sides, and then both on the tooling and the simulation and things like that. And the idea is that on the virtual level, try to understand what the opportunities are. Then you refine and evaluate the whole thing until you get more and more physical. And at the end, you have a product that consists of both software and physical solutions. Model-based software engineering is more specific than only, or model-based systems engineering is more specific than only systems engineering, because it means that you use models in many of these activities. And the term model is itself interesting, because when you look at the term and try to find what models actually are, then we identify that there are an awful lot of models, and probably most of you know that already. If you look at this, I have shown examples from different domains here. Interestingly, if you look at the top row, you see models of very big things like galaxies and galaxy structures, down to atoms, where in the middle we have the Earth, we have humans, we have genes and all this kind of stuff, and even the coronavirus is there. But the top row, these are all scientific models. And scientific means that scientists try to understand the world. So if the model does not correctly conceive to the world, then the model is wrong. And the lower row are engineering models, though the engineers usually use their models to design something. And if the model doesn't finally fit to that what is there out in the world, then the world is wrong. Actually, the car, the building is wrong. And so this is a difference between engineering and science models. But we are going to engineering models now. Actually, we don't only look at models, because modeling is something which is very prevalent everywhere. But when we look at computer science, they have invented the notion of language, of model language. And we have an awful lot of languages out there. Some of them that are mentioned here are programming language, which in a certain kind of, it can also be seen as a variant of modeling language, but UML is of course pretty dominant in the early phases of modeling things. State charts can both be used as model or as a programming language. In the systems domain, the situation has become also very interesting. We have modeling languages for computer-aided design, computer-aided manufacturing. We have a lot of simulation languages out there. SysML has become very interesting recently because maybe you know that UML is not, it has its share, but it's not used as much as needed, or people have been thinking early of, because particularly in software engineering, agile methods are to some extent pretty dominant, and agile methods do not model that much. What they do is they try to fit the informal analysis results directly into code. In the physical world, the situation is slightly difficult because this idea of evolution doesn't work that easy, because if you have the physical gadget out there, you cannot just easily change it. This is easier with software, at least theoretically. So SysML is actually becoming pretty interesting, and SysML has started off, maybe you know that, as a specific derivative of the UML, the system modeling language, has been evolving over time. And meanwhile, and this is pretty interesting, and this is one of the hints that I takeaways potentially for you, is when you are in the domain of Internet of Things, cyber physical systems, SysML is now being developed in a 2.0 version, which is specifically and for SysML, for systems. It includes a lot of physical, or it will include a lot of physical and geometrical modeling constructs, and it will be independent of the UML. It will become a standalone language and not only a derivative of the UML in itself. So there's a lot of interesting things going on in that area. But still the main problem is, or one of the bigger problems is, what are we going to do with the models? And so if you actually have models, just for documentation is not enough. We want to do analysis, try to understand what the actual problem is. We want to do design by structuring the system that we are going to develop. We want to do simulation by understanding whether the system really does what it is. In software, we usually do automated tests. In the systems domain, simulation of the physical and the computational part is of course interesting. Rapid prototyping is a potential use case for models, of course. Dimensioning of the system, the physical part, by trying to reduce the weight or something like that, by changing structure a little bit, that has under the term additive manufacturing already been quite helpful. Potentially, we are able in the future to also print our systems, not only the software being generated, but also the system by 3D printing, and together with code generation and synthesis and so forth. So we potentially could actually just model our system, push a button, and have it implemented. There's a lot of possibilities to deal with, but if these possibilities only work if we have a sound, grounded theory for the models. We have been experiencing that quite a lot. If you just use models as drawing tools and have an informal understanding, that's okay. But if you want to make more out of that, you need some kind of theory behind that. You know, mathematicians and physicists have a very well grounded theory, and theory also means that you're not only drawing your models, but you know what it means if you evolve them. You know if these models are inconsistent to each other, or if the models are some kind of one model implies another and things like that. So you need to have toolings, evolution techniques on this, and math is a perfect example for that, but it has taken hundreds of years to go that far. So if we come up with modeling languages like SysML, or maybe even domain-specific languages, we need techniques on it. We need tools that help us to evolve the models in an effective way. What does that mean? We, if we have models, we need a syntax. We need things to represent that. We need to understand what the model means, and we need a mathematical theory below that. And in the cyber physical systems domain, it's an interesting question what a potential theory for that could be. And I'm going to investigate that a little more and trying to connect this theory with practical questions. But before I do that, I want to share one additional notion that if we have this theory at hand in an appropriate way, you could, for example, think in computer science, we have state machines. And we have a lot of algorithms that help us to understand whether state machines are doing what we want them to do. The most important thing is actually automation. Automation of development steps. Brand has coined that very nicely last year again, and he says that automation is really the most effective thing that helps us to improve both productivity, which means efficiency of the developers, as well as product quality. And we can automate so many things. We know that in computer science already by having build scripts that do a lot of things for us. And the build scripts connected with analysis tools on the code level are things that are helpful. We need that on the modeling level also as well. And our systems engineering colleagues do have already only isolated, but they have these kind of things as well, where they automate steps, where they do optimizations in an computational form, usually using simulations and trying to guess and improve parameters for their thickness of any kind of things, and height and weight and stiffness and so on and so forth. Automation is really the key here, which also means that we have the possibility to repeat steps. We can evolve our requirements and run them down to the implementation through the models as quickly as possible. So we are trying to find out what is a good notion of what the semantics, the meaning of these models that we need in systems engineering are. And looking at various approaches, we finally identified that there is a common ground that says that actually it's not the system, the physics itself that is of interest. What is of interest is actually this notion of that the system realizes a function. A train, for example, is not in itself interesting. The train is interesting because it gives us mobility. A car is interesting because it gives us mobility on a very individual form. Okay, we can also store things in the car, but basically mobility. Smartphones is not itself interesting, but it gives us communication, photography, possibility to play games or whatever we do. And actually our mechanical guys, there is a larger approach here. They are thinking of systems realize functions. And this notion is actually interesting quite a lot because it's primarily the function that they specify in the requirements. And then they decompose this function idea into a design and finally realize individual components. And the physical geometry is actually something that follows the function, ideally. In practice, it doesn't do that always, but ideally, that would be the thing that is needed. So looking at this notion of function is actually interesting because and this is something that we see in mechanical engineering books once in a while. It says that any cyber physical system is something, actually the thing is already 20 years old, but and it wasn't called cyber physical system but any system is something that takes energy, material, and data and maps that through its function to other kinds of energy, material, and data. We can also say instead of data, signals or things like that. So, but when you look at this over time, so we have flows of energy, material, and data coming in, and flows of energy, material, and data coming out. And to our experience so far, this concept carries pretty far. It helps us actually to describe physical things like heating water or something like that, or also transforming water into ice, or making chemical connections, and also data things. And there's interestingly two completely independent approaches. There's this idea of principal solutions that have a physical and a geometric solution itself. And on the other hand, there is an approach that we call CAN networks that have been put much further through Manfred Roy in Munich, where flows of data are mapped, input flows of data are mapped to output flows of data. And the challenge that we see at the moment is that we have to bring these things together, and then we have actually a universal specification and construction principle, because that helps us to actually understand and in particular specify any kind of cyber physical system. Some examples to keep it not too abstract. Very simple examples. This, for example, is the adding function. If you have a stream of naturals coming in on the X and a stream of naturals coming in on the Y ports, then they are added and you get a stream of sums out on the Z port. I guess pretty simple. But this is something that we can, for example, specify in our computer science area. On the electrical circuits area, they have the very same notion. The idea is not the circuit is the most interesting thing, but what is actually coming in this terms, electrical power or not, binary zeros and ones, and what is going to be produced on the outside. Physical functions actually work pretty similar. Here, this is a small physical function that actually stores water in a reservoir, and you can use this principle to describe how that happens very simply on for this water. I don't know the English word for it at the moment. For the dam, where you have a lot of water in it, or also for small barrels where you just put rainwater into it, or for other things like that. So you have a contact area A, and in this area you receive the water, and there's another area we call B, where the water is going out away, and we have a tap in between, and the tap actually is binary. It says it's open or closed, which helps us to store the water or release it if you want to. And we can describe that, of course, using traditional functional physical functions, very simple. The point actually is here that with this description, we do not describe software anymore, but we describe a combination. So we have a slight combination of software. Probably in this water reservoir, there is some electrical gadgets and some software gadgets in it, but the main function is storing water for a time and releasing it upon request. And these simple things, for example, can of course also be connected if you want to. We can use the same principle. By the way, if you look at the principle, you see that the function has an interior, which we don't really know what happens inside the water reservoir, but it has an interface. And the interface is the things that are flowing in and the things that are flowing out. We can use that for energy as well. Here, for example, we have a friction gear. And the friction gear, again, physically simple, but the friction gear does the following. It actually transports energy and transforms energy. And from a functional point of view, the friction gear has an input, which is contact point A on the small wheel, and it has an output on the large wheel. And if there is energy coming in terms of rotation and friction and torque force, then the wheel starts turning and gives the energy back on the contact point B. In the same amount of energy, we know that because energy cannot be lost, but in a different in different speed and different torque. So, and this is a typical elementary function. Yeah, you see that there's a lot of possibilities to combine these things because we connect this wheel with other wheels, and then we get possibilities to translate kinds of energy in different other kinds of energy, or heat, or stored energy in that sense. Our mechanical engineering guys have a catalog of around 300 functions of that kind. I don't believe that, and my colleagues that I talked with believe is that this is a complete list, but it's good. Yeah, the list covers a lot of possibilities, warm things up, translate energy, and things like that. And this is very similar to what the software engineering people do with design pattern. These are core elements, and the core elements have a well-defined interface, and this interface helps us to actually connect these things. And we see this, for example, in the next picture. This is a very abstract picture of what a company does. A company takes raw materials and produces, for example, cars. And of course, it also takes data. It gets orders, and it produces information and advertisements and things like that. And the company is of course structured internally. And the idea is that all of these things are, in that term, functions that that describe what actually happens with the input and how it is translated to output. And this idea, a notion of function, works in the computer science area at the moment. It works in the mechanical area quite well, because there is, of course, ideas on how to handle these things. And we need to bring it better together, and we need good modeling languages to actually describe these things as a semantic background. And SysML is currently an attempt to go in this direction. Maybe very shortly, because time is already going on, important is, of course, that we need to be able to have under-specification available. Under-specification means that we don't have to describe everything in detail already when we only talk about requirements. Under-specification is well known, for example, from state machines, where we have the possibility, from non-deterministic state machines, where we have the possibility that a transition, or that there are several transitions reacting on a certain input. And if we take that not only during runtime, but we say, okay, this is a design principle where I say I have choices, and I don't know whether the choice is actually handled at runtime, handled through different variant configurations, or handled during design time, where someone decides which transition has actually been taken. This is something that is needed. And on the physical level, they do that similarly by describing, for example, a differential equation with certain unknowns in it. A small constant c that are somewhere added and said, oh, I don't know too much detail, but it's small. And I also talked already about composition. That is another important principle. And we currently see two different kinds of composition. There is this functional decomposition paradigm, and there is a geometric decomposition paradigm. And currently, that comes from pure manufacturing, they mainly think in geometric decomposition. You see the car decomposed in a lot of its parts. And we think much more of functional decompositions, where we put things together and get bigger services, larger function, whatever we want to do that. And we have to marry these two things. They don't fit together too well, but there have been good examples that show how this can actually work. Yeah, decomposition enable reuse. I guess we all know that. If we don't decompose well, we are not able to come up with smaller individual solutions and also reuse individual solutions in our decomposed structure. What do we have? We have this notion of function that transforms energy, material, and data. And actually, if we look at that in more detail, if you go into mathematical structures, which I didn't do so far, then we have a lot of foundational challenges. Computer science is discrete. That just means that we see here 4 time lines. The lower 2 are typically from computer science, and the first one as well, where the ticks mean actually time is continuing in time slices. But physical things are typically continuous. And to put this well together is not so simple. In former times, computer were slow and physical processes were rather quick. So the combination of these 2 kinds of time progresses was typically forced by, okay, computers need to be high prioritized and maybe needed to be able to interrupt each other because a process with higher priority is coming in. Nowadays, the situation is typically the other way around, that computer is pretty quick, and the real physical world doesn't change that much in when computation time takes over. And then, for example, that you can idealize that the computation is done in instant time, and then physics continue, and then again computation is instant time. But actually both is not entirely true. Both is an abstraction of the real world. Sometimes physical processes, like in a crash or in an atomic simulation, are pretty quick, and sometimes, like for example in a simulation of a climate world where you simulate 50 years, then the computation time is much quicker. So challenges are here. And we have, as I mentioned already, the challenge of bringing physical and physical geometric stuff, material stuff, and functional stuff together. Again, we don't have we have many single solutions for individual domains at the moment, but we have to generalize that so that we are actually coming up with good tooling, with good notions to bring all these things together, so that we are finally able to describe this kind of cyber-physical system, which is probably a factory that takes screws and produces cars and takes a lot of data from outside and produces other kinds of data. So there is it stays challenging. I didn't mention digital twins at the moment, which is of course also important. To my belief, for example, a digital twin should be part of the cyber-physical system, even so it's physically distributed and not, so the digital twin of a car is not running with the car, but it's strongly connected. And thinking that in a holistic way is probably better than isolating things and doing that in individual ways. Which brings me to a wrap up. Holistic is important. We need languages like SysML. I didn't speak much about domain-specific languages. I could say much more about that. I have introduced these 3 universal construction principles. The idea what a function is, that we need controlled under specification, and we need composition of this function concept, which, by the way, mathematics brings with us when we know what the function really is. We need, of course, then build on this development processes, tools, and of course then tools that help us to automate as much as possible to stay agile and productive. Thank you very much for your listening. As Manuel already said, if you have questions, you can either post them or potentially also say them. I don't know. Manuel, I hand over to you.